Okay, we're going to spend some time now talking about vectors. Remember, a vector is anything with a magnitude and a direction. So, position is a vector. Say 5 meters to the right, 10 meters up. The meters, the 5 meters, the 10 meters, that's the magnitude. The direction is to the right or up or at an angle. Displacement is also a vector. What's the difference between position and displacement, by the way? They are different things. Position versus displacement. Okay, so position is where you are at, period, relative to your origin. Right. Displacement is delta x. Displacement is where you ended up relative to where you started. It is possible that they can be the same thing. If you started at your origin and ended up somewhere, then the displacement and position would be the same thing. But if you started at, say, 2 meters to the right of your origin and ended up 10 meters to the right of your origin, the position would be 10 meters to the right, but your displacement would only be 8 meters, because you only moved 8 meters relative to where you started. Okay. Either way, they're both vectors. They have a magnitude, how long, and a direction associated with them. Velocity is a vector, how fast and in what direction. Acceleration is a vector. We're going to talk about forces. Forces are vectors. It depends how something responds to how you push on it, depends upon how hard you push and in what direction you push. So force is a vector. There are a number of quantities we're going to talk about that are all vectors, so we need to know how to work with vectors. So a vector. Let's say we have a position vector that's, like I said, 10 meters to the right. How long I draw the vector represents the 10 meters. The right is the direction. Now, there's two ways to write vectors. We can write vectors in terms of a magnitude and direction. By the way, this is our polar coordinate system. So to write this vector in terms of a magnitude and direction, we would say 10 meters, comma, direction is an angle. So traditional coordinate system, if you think you're a polar coordinate system, where is the angle always measured from in a polar coordinate system? The 0, the positive x-axis. So this lies on the positive x-axis, so our angle would be 0 degrees. So that's one way to write our vector. The other way to write the vector is in terms of what we call vector notation. Vector notation is related to our Cartesian coordinate system. Our Cartesian coordinate system, if the origin was at this end, this is the position of our object at this end, we would have 10 meters in the x direction and 0 meters in the y direction. Now that's not quite vector notation though, but those are the pieces of information we need to know. To write the actual vector in vector notation, we use what are called unit vectors. To represent the x direction, we use a little unit vector. By unit vector, I mean it has the length of 1, and it points along an axis. So in the x direction, we use I hat. It has a length of 1, but it points specifically in the x direction. For the y direction, we use j hat. For the z direction, we use k hat. So j hat has a length of 1, but it points in the y direction. K hat has a length of 1, but it points in the z direction. So to write and use these unit vectors to write our vector in vector notation, what we would say is we'd take the x component, 10 meters. Since that's the x component, we would say 10 meters I hat. Plus, the y component is 0, so 0 j hat. And technically 0 k hat as well. Now we don't tend to write the zeros in. I mean 0 times anything 0. So we would write this vector as 10 meters I hat. That would be vector notation. It tells us what the length of the component is in that specific direction. This particular vector lied along the x-axis, so it only pointed in the x direction, and that's why we only have the I hat term. The j hat and k hat terms are 0. Okay. Questions so far? Let's say we have our 10 meters, but this time it's oriented at an angle of 40 degrees above the x-axis. So to write this vector in terms of magnitude and direction, that one's easy. It's going to be 10 meters, comma, 40 degrees. So that is that vector in terms of a magnitude and direction. The magnitude is 10 meters. The direction is 40 degrees. Let's write it in vector notation. When we want to write our vectors in vector notation, we need to break our vector into what we call components. The components are always parallel to the axes. So traditional coordinate system, x-axis horizontal, y-axis vertical. We need to draw sides. One side needs to be horizontal and one side needs to be vertical. Easiest way to do it is start at the end. Draw, it doesn't matter which one you draw first, the horizontal one or the vertical one. If you draw the horizontal one first, you draw all the way over until you're just below the tip. And then you draw the vertical one up to the tip. The components have to meet at a right angle. Now you certainly could have drawn the vertical component first until you got level with the tip, and the horizontal one. Either way, the components have to meet at a right angle. The x component is the one that's parallel to the x-axis. So it's this one or this one, whichever way you like to draw it. The y component is the one parallel to the y-axis. So it's either one of those. Okay so far? We need to find the values of those. In order to write it in vector notation, we need to be able to figure out the value of the x component and the value of the y component. Well, we know the hypotenuse. Notice once we draw the components in, we have a right triangle, regardless of which way we drew the components in. So with the right triangle, if we know the hypotenuse and the angle, we can certainly find the sides. So the x component, this side is adjacent to the 40 degrees. Which trigonometric function deals with adjacent and hypotenuse? Cosine. So we have the cosine of 40 degrees is equal to the x component over the hypotenuse, 10 meters. So our x component is 10 meters times the cosine of 40 degrees. Let's go ahead and get a numerical value for that. I'm going to keep a couple decimal places for now. 7.66 meters is the x component. The y component. The y component is opposite our 40 degrees. So we want sine. The sine of 40 will be the y component over the hypotenuse. So the y component is 10 meters times the sine of 40. 6.43 meters. So this 10 meter long vector at an angle of 40 degrees is equivalent to traveling to the right by 7.66 meters and up by 6.43 meters. We can start and end in the exact same place either by walking 10 meters that way or by walking 7.66 meters this way and 6.43 meters that way. We get to the same location. So vector notation. Our vector, we have 10 meters at 40 degrees, or we have 7.66 meters I hat plus 6.43 meters j hat. Two ways to explain the same thing. So 10 meters at 40 degrees is the same thing as 7.66 meters I hat, which means the extraction, plus 6.43 meters j hat. Two ways to explain the same vector. The top way is the magnitude and direction as a number, a length, and an angle. The second way is vector notation. You need to know which of these mean. You're going to be asked for magnitude and direction, or you're going to be asked for vector notation. So you need to know which is which and how to get both of them. Okay. Questions on that one so far? What if we went opposite? What if we started here and went down by 10 meters at an angle of 40 degrees below the negative x-axis? Drawing the components, we have to go left and down to get there. So what's my x component? My y component? Okay, so let's write our vector. In magnitude and direction, what will it be? Magnitude and direction, 10 meters.
220 degrees.
220, right? Yeah. So magnitude and direction is the 10 meters and 220 degrees. Vector notation would be the negative 7.66 meters I hat minus the 6.43 meters j hat. The negative sign on the x component means you had to go left. The negative sign on the y component means you had to go down. So you can always get the sign by starting at the end of the arrow and trying to get to the tip of the arrow. You have to go either left or right and up or down. On this one we had to go left and down, or we could have gone down and left. That'd be fine. But it's still down meaning negative y and left meaning negative x. So we get the same sign either way. Let's see. Let's say we're going on a field trip. Hey! So exciting. Let's say the first leg of our field trip tells us to walk 10 meters north. And then the next leg of the field trip tells us to walk 5 meters east. And then finally, we need to walk 2 meters so 2 meters at 30 degrees south of east. So these are our instructions. What's the final position, or what is our final position after we've completed these 3 legs of the trip. Where are we ending up relative to where we started? Relative to our origin. So we have 3 vectors. This vector is going to be 10 meters long and point upwards. This vector is going to be 5 meters long and point to the right if we're using traditional north, south, east, west. This vector is going to be 2 meters long and it's going to be 30 degrees south of east. So basically what we're doing is we're going to be adding these 3 vectors together to find out a final position relative to where we started. To add vectors together, you simply draw them head to tail. So you draw the first one. This one has a length of 10 meters. You draw the second one. This one has a length of 5 meters. The second one, you start at where the first one ended. Whenever you're adding vectors, you always start at where the previous vector ended. To add this last vector in, we need to go 2 meters at 30 degrees south of east. That vector is the result. If we draw a resultant vector that starts at the same place the first vector started and ends at the same place the last vector ends, this is our final position vector. In this case, since we're going to go ahead and call our starting point the origin, our final position vector is the same thing as our displacement vector. Because we started at the origin, we'll end up over here. So basically, we need to describe this vector. Where did we end up relative to where we started? How long is this? And, what angle is this? That's what we're looking for. We're looking for r, how long it is. We're looking for theta, the angle it's at. So can we simply say 10 plus 5 plus 2, so we're ended up 17 meters away? No. Unfortunately, that doesn't work. So these 3 vectors, these are given in terms of magnitude and direction. Magnitude, direction. In order to find the magnitude and direction of this final vector, we need to figure out finally how far east we've ended up traveling and how far north we've ended up traveling. Basically, we need the components. This vector has an x component, this vector has a y component. We need the 2 components in order to work backwards and find the hypotenuse and the angle. The nifty thing is with vectors, if you write your vectors in vector notation, you can simply add them up very nicely. So for example, our first vector, this one right here, has no x component, and it has a y component of 10 meters in the positive y direction. So that is the vector notation of our first vector. Vector notation of our second vector, it's 5 meters in the x direction, 0 meters in the y direction. Our third vector, on the other hand, has both an x and a y component. If I started in the same place it starts, I have to go to the right and down in order to represent that vector. How far to the right did I have to go? So to the right, the x component. Are we adjacent or opposite the 30 degrees? Adjacent. So it's going to be the 2 meters cosine of 30 degrees. So 1.7 meters. The y component, we have to go down, so it's going to be negative. 2 meters, we're opposite the 30 degrees for the y component, so 2 meters sine of 30. So that's going to be negative 1 meter. So this third vector can be written as 1.7 meters I hat minus 1 meter j hat. So totally, how far have we gone to the right, or the east in this case? 6.7 meters, the 5 plus the 1.7, the 5 plus the 1.7. So 6.7 meters in the x direction. How far in the y direction? 9. So we went 10 and then came down 1. So total 9 meters in the j direction. That gives us the components. Our resultant vector has an x component of 6.7 meters. It has a y component of 9 meters. That's fantastic. We know the two sides. If we know the two sides, we can easily come up with the hypotenuse and the angle. So this here is our answer in vector notation in terms of components. How are we going to get the hypotenuse? Exactly. Pythagorean theorem. 7 point what? Thank you. So R, we've ended up a total distance of 11.2 meters from where we started. Theta. Well, if I have the opposite side and the adjacent side, I know the tangent of theta is the opposite over the adjacent. So 9 over 6.7 inverse tangent (53°). That would be our vector in terms of a magnitude and direction. So we've ended up a total distance of 11.2 meters from where we started at an angle of 53 degrees. So that's 53 degrees north of east. You all right with that?
You don't write meters on one column.
Oh, yes, we do. Sorry. Thank you. We do need the units. So 11.2 meters, 53 degrees. Whenever you want to add vectors, and actually if you want to subtract vectors as well, you need to write the vectors in terms of vector notation. Did you notice this final x component had absolutely nothing to do with the individual y components? It was only dependent on the individual x components. The final y component had nothing to do with the individual x components. It is only related to the individual y components. That's always going to be the case with vectors. X components determine x components. Y components determine y components. They're not interchangeable. So your final x component will simply be the sum of the individual x components. Your final y component will be the sum of the individual y components. If we were to do this in 3 dimensions, the final z component would be the sum of the individual z components. So in order to add vectors, or subtract vectors, quite honestly, or, now we can't multiply vectors in a normal way. We'll talk about how we can multiply vectors, but they have to be written in vector notation as well. So you always need to write your vectors in vector notation prior to doing anything with them, basically, before you add, subtract, divide, multiply, that sort of thing.